Okay, so in this section, we're going to talk about the inverse of a matrix. So this is section 2.6, the inverse of a matrix. But I first want to talk a little bit about what exactly it means to be an inverse of something. So, you've heard this term a lot in your life. So if I ask you, what is the inverse of the number 2? You'd say a half, right? So you know that 2 times 1/2 is equal to 1. So we know that we're able to find a number such that the original number 2 can be multiplied by it to give me 1, which we call the identity. So 1/2 is an inverse of 2. Great. Really quick review there. That's all. And so we've talked about inverses in other math courses. You talked about inverses of functions. We've kind of been using the integral and the derivative as inverses as well. So it's not surprising then that a matrix itself should be able to have an inverse and actually be pretty helpful to us as mathematicians. So there's an E on the end of that. So if I give you a matrix A, how can you find the inverse A? So what we need to do then is we need to find, something such that when we multiply A by it, we get 1. Now, what is 1 in matrix form, right? If you multiply A by an A is a matrix, multiply it by another matrix, you're not going to get a number, right? So instead of writing 1 on this right-hand side, we actually write the identity matrix, which we know to be equal to 1s all down the diagonal and 0s everywhere else. So I want to find something here. In the meantime, I'm just going to call it A inverse like this. So the inverse has the -1 sign, like you've seen in algebra for functions. And there's a very specific process by which you find A inverse, but I want to talk about why we care about it in the first place. So one of the main reasons we actually care is because it has the potential to make our lives a little easier. So let's take an example for just, a problem you might have had in your past. So you might have e to the x is equal to 2. How do you solve this type of problem? Well, you need to use the inverse of e to the x, which is natural log. So you're going to use it to undo this e to the x term. So you take the natural log of both sides is equal to the natural log of 2, and then the left-hand side just becomes x because it's an inverse, and just like that, you've solved your equation. So similarly, we've been working with equations like this. Ax is equal to b. So we have, once we've encoded all of our system of equations into our matrix, we can write it in this form. And we're trying to figure out what x is. X is our variable here. And so we can kind of do exactly what we did in the case of e to the x, but we can use matrix inverses instead. So if I'll rewrite this, ax is equal to b. If I instead multiply both sides of my equation by A inverse, aka take the inverse of both sides, apply the inverse to both sides, then you'll notice here that A times A inverse we've defined to be identity. So I know that this left-hand side is just equal to 1 times x, or x, and then my right-hand side is equal to this mysterious A inverse times b. Okay, so that's great. And, how exactly does that help us at all? The reason is, to find x like we're normally used to, we have to do a ton of row reduction, right? So you'd have to go through and you do those permutations and the additions, the multiplications to figure out what x is by reducing your system, right? Here, as you can see, we're actually able to figure out what x is simply by a product of two matrices, which is super, super helpful. And it will remain helpful on exams and stuff that you understand this concept here. But what's actually kind of a bummer is that I haven't told you how to find A inverse yet. but the process by which you find A inverse involves row reduction. So there's really no escaping row reduction anyway, because you're going to have to do it to find A inverse in the first place. But a lot of the exam problems are set up in this form as I've written it before you, so you might as well get used to the concept that you can take this step here pretty well. Okay, so how do you actually find A inverse? So to find A inverse, there's this very specific algorithm. So you form an augmented matrix. So we've worked with these before. You put A on this side. Then we're going to do something a little funky here. We're going to put the identity matrix itself on the right-hand side. So you may be thinking, oh, but we've only put, one column on the right-hand side. Yeah, that's true, but as you do the row operations, it will still apply to your entire row, and you're actually allowed to tack on extra columns here and here and here and blah, blah, blah. So this is totally valid for us to do, and it actually makes our lives a whole lot easier. Then what we're going to do is we're going to row reduce this entire matrix here, which is going to be, sometimes a pain on exams and stuff. And then we're going to row reduce it until we get identity here. And then what's actually really cool is that A inverse pops out on the other side. So really, as long as you know how to set this up and you feel comfortable taking row reductions, you'll be able to find A inverse pretty quickly. Or not quickly, but easily. It's just sometimes the way they frame questions on exams, which can be pretty difficult. So here, I'm going to move this down a little bit. We'll get to that in a second. So let's go ahead and just do an example. Let's take an example. So if A is equal to just a 2 by 2, 2, 1, 1, 4, what is A inverse? Okay, so I'm going to form this augmented matrix here. So I'm going to write 2, 1, 1, 4. I'm augmenting it with the 2 by 2 identity matrix here. And I'm going to row reduce it until I get identity on the left-hand side. So first thing I'm going to do, I need a 1 in the upper left, right? So I'm going to switch my 2 rows here. And I have to remember to take this part of my row with me. It's very easy to mess that up, especially with 3 by 3 cases. I'm going to move, I'm going to move my top row down, and I'm going to record it so my grader knows what I just did. Now I need to get rid of the 2 here. To do that, I'm going to subtract 2 times the first row from the second row. So row 2 is going to become row 2 minus 2 times row 1. So I have my top row that remains the same. I have 2 minus 2 times 1 is 0. I have 1 minus 2 times 4 is -7. I have 1 minus 2 times 0 is 1. And then I have 0 minus 2 times 1 is -2. Okay, great. Let's see here. So I don't really want to do fractions, but I think I'm going to have to. So I'm going to go ahead and divide my last row here. That's a z. I mean the 7. My bad. Times row 2. I'm actually going to go ahead and make that negative. So this is being difficult. There we go. So I'm going to go ahead and make it a -1/7 just so I can get rid of the negative sign as well. So I have 1, 4, 0, 0, 1 up here. This becomes a 1, obviously, because I wanted it to. And then I have -1/7 here and +2/7 here. Great. So the last thing we need to do is get rid of that 4. So to do that, I'm going to do row 1 becomes row 1 minus 4 times row 2. So that will get rid of that 4 for me. So I have 1 minus 4 times 0 is 1 still, which is good. 4 minus 4 times 1, like this. 4 minus 4 times 1 gives me the 0 I needed. Great. 0 minus 4 times 1, negative 1 over 7 gives me a positive 4 over 7. And then 1 minus 4 times 2 over 7 is 1 minus 8 over 7, which gives me negative 1 over 7. 0, 1, negative 1 over 7, and 2 over 7, right? Because the bottom row stays the same. Am I done? Oh, what happened here? Yep, looks like I'm done, right? So I have the identity on my left-hand side here. Great. And then I have what appears to be A inverse on my right-hand side. So A inverse then is equal to 4 over 7, negative 1 over 7, negative 1 over 7, and 2 over 7. Okay, great. The cool thing about inverses is they're actually pretty easy to check. If you have the time on an exam, you're able to just plug A inverse back in to its exact definition. So A times A inverse should give me identity. So you're allowed to check if you wish. And it should work out. In this case, it will. So there is one other thing. There's a little trick for finding the inverse of 2 by 2 matrices. So there's a formula. I'm not actually sure if it's in the textbook. If not, it should be. If A is just any arbitrary 2 by 2, A, B, C, and D, let's say, then there's a formula. A inverse is equal to 1 over AD minus BC. And then what I do with the entries is I flip the two diagonal ones, so A becomes D, D becomes A. So all I've done is I've moved these two. And then B and C stay exactly where they are, but they become negative. So, someone a long time ago figured this out. It'll make your life a lot easier. Put this on your formula sheet for sure. Let's go ahead and just actually check and make sure this works. So we just did a 2 by 2 case, so we should be able to get this formula to work out. So I have A is equal to 2114. Then A inverse should be 1 over A times D is 8, minus 1 is 7. Great. And then my 2 and my 4 switch places, so I have a 4 and not a 7. Whoops. And a 2 down here. And then I have a 1 and a 1 that remain where they are and just become negative. So as you can see, if I were to distribute the 1/7 in here or, out here, these match up perfectly well. So I'm content that the formula works. I'm also content that we did the row reduction properly. And that's just the algorithm for finding the inverse of a matrix. So it gets more complicated a little bit as you go to 3 by 3 cases, but it's, same process. So I just wanted to do a quick example problem from an old exam. This is from an old final exam. I didn't record exactly which one it's from, maybe 2015. So we have, an unidentified matrix R, such that when I multiply it by, my column vector x, y, and z, I get another column vector, which they've defined here. And then I have to figure out what R inverse times a specific vector is. So there's a lot going on in this problem, but first things first, we need to figure out what R is. We're not going to figure out what R inverse is without R. So I have this property here that, so R is some matrix here. I multiply it by x, y, z, and I get x plus 2y plus 3z, y plus 2z, and z. So what I like to do when I have to set up something that looks like this is I like to make sure the sizes are going to match up. So I don't know exactly what size r is. If you get really good at this, you can guess immediately. But I know this xyz vector here is a 3 by 1. And what I'm left over with is a 3 by 1 as well. If I was able to multiply these two matrices together in the first place, I need my number of columns to be equal to the number of rows of this one. So I need a something by 3. And then I need the number of rows as well to be equal to the number of columns in the remaining, the term on the right-hand side of the equal sign. So I need 3 by 3 here. And we can check again, because that was kind of rough, that these add up. So these have to be equivalent, right, which is great. And then the matrix that remains is 3 by 1, which is exactly how we have it set up. So, even if you don't write it out like this, it is just good on exams to get a sanity check and make sure your matrix that you're looking for is the right size. So anyway, we're looking for a 3 by 3, and it's pretty convenient for us actually. We're able to just read off what the entries of R should be. So I know that if I multiply my first row of R here by x, y, and z, I get x plus 2y plus 3z. So I know that if I want to get that, I need 1, 2, and 3 to be my first row. Similarly, we just need a 0, a 1, and a 2 for the y plus 2z term, and then all I'm doing in my last row is taking my z term. So I need 0, 0, 1 there. So this right here is equal to R. And then to go through and actually figure out what R inverse is, you're going to do row reduction and a lot of it. So we go through, we augment my matrix R with the 3 by 3 identity. And I'm not going to do it on screen, but I'll give you the final result so you can check if you'd like. And when I did it, I got identity on the left, which is what you should get. And then on the right-hand side, I got 1, negative 2, 1, 0, 1, negative 2, 0, 0, 1. And so this right here turns out to be R inverse. And so R inverse times, what was it? 1, 2, 3 gives me 0, negative 4, and 3, which was option G, I believe. Yep. Okay, so this is just, a couple more example problems on how to actually find the matrix. Like I said, just follow the algorithm and you'll do fine. And just remember that this right here is important to understand for exams.